Welcome to High Tech Heroes, the program that takes you behind the scenes of today's high-tech industries, where you can meet the people and examine the ideas creating tomorrow's technology. And now, coming to you from the studios of Foothill College, high atop the mountains overlooking Silicon Valley, here's your host, Sherwin Gooch.
Ni hao, I'm Sherwin Gooch. Welcome to High Tech Heroes. Our episode this week is the final installment of a three-installment speech by the world-renowned supercomputer architect, Seymour R. Cray. As you may recall, 2 weeks ago, Mr. Cray told us how he designed circuits to work around the varying performance characteristics of components made from non-uniform gallium arsenide material. Then, last week, he discussed many details of the construction and architecture of the soon-to-be-released Cray 3 supercomputer. This week, he's going to attempt to answer questions from the audience. So now let's watch these young upstarts play Stump the Stars with the world's greatest living computer architect, Mr. Seymour Cray.
Tell you just a little more about what's happening right now, and then if you have some questions, I'll be happy to make up answers for them. What has happened in the past year is that the Cray 3 program got up to the point of building prototype modules, which more or less worked. But as we looked at the production problem, we didn't have enough production engineering experience as the project was constituted in Chippewa Falls to address the robotics required to manufacture the machines in volume. Parts are so small, the vertical jumpers that I talked about are invisible. I mean, you really can't see what you're doing. So hand assembly does not really look practical except in an experimental mode. Besides that, the population is very large. We have 12,000 of those vertical jumpers in that 4-inch area. And so we need automatic assembly equipment which manufactures the jumpers on site. On site here means within a couple of inches, and puts them in the board, cuts them off, does the whole thing. Well, let me describe the jumpers for a minute and you appreciate the problem. Jumper diameter is 4.8 mils. That's very tiny. It consists of 7 strands of beryllium copper wire that are gold-plated. It's the bundle diameter I'm talking about, it's 4.8 mils. Well, what we have to do is we have to weld these every 32 mils and then grab the welds and untwist the bundle to make sort of a birdcage effect so that as the jumper is pulled through the board, the bird cages line up with the board barrels. We use the barrel of the board for one side of the connection, and the 7 strands of wire all making contact with the barrel makes a high-quality connection. So the way this is done is with laser welding, laser cutting, but it's all done in a very, very tiny area. These are made by Hughes, these machines that we're getting, made by Hughes. They provide the mechanism for moving the wire. Coherent General is currently making the laser system so that this machine will take one of these modules with the boards loosely stacked and go on a platen, go into this machine, and this machine puts in 12,000 jumpers that it makes as it goes, does the whole thing without human intervention. So there's a challenging problem for robotics. We haven't got this running quite yet, but we have prototypes now that are coming online. We're very optimistic this will happen in the next couple of months. That has been pacing. And as I said, we had problems simply with the human resources to do this work in Chippewa Falls, so we moved the project to Colorado this summer. I've moved to Colorado Springs, finding out about mountains now. It's quite a lot different than the flatland in Wisconsin, and thoroughly enjoying it. One of the reasons that we picked Colorado Springs was that there's been sort of a recession there for 3 or 4 years. Primarily defense cutbacks, I believe. But there were thousands of technical people there unemployed, and they didn't move away. They liked Colorado Springs, and they stayed there, pumping gas or whatever. And so when we moved into town, we didn't run an ad, But the local paper printed our picture, and we had 3,500 applications. It was wonderful. The real challenge was trying to process all those people to make the best possible choices. It was a very pleasant experience, so pleased with the move. There was some time lost with the move. As I view it, we lost 3 months in moving from Wisconsin to Colorado. But the additional resources we have now are several-fold what we had in Wisconsin. So I believe we have closed the gap, so to speak, on the move. I think we lost another 3 months related to plateauing without having the facility in Chippewa. So in my mind, this project has slipped about 6 months since we originally envisioned it. We were originally planning to deliver machines in the second quarter of 1989. It looks now like we'll deliver them in the fourth quarter of '89. But we're gearing up for production, so we hope to have a steep front end when we start delivering them. So, thank you, and are there any questions?
Could I start with a question?
Please.
My name is Jim Almond. I'm from the University of Texas Systems Center for High Performance Computing. Maybe I could begin the question with a reference to history, like you would understand. The 60-bit word length on the control data machines caused quite a little bit of problem and consternation migrating into the future, and now we enjoy a 64-bit word length. I have 2 questions about it. We're trying to establish teamwork between large-scale computers and scientific workstations. They also offer 64-bit words, but usually according to an IEEE standard for the structure of a floating point word. Is there any chance that we can enjoy a mainstream floating point word structure according to the IEEE standard on our large-scale computers? Is the first question. The second one is, many of our users seem to think that even a 64-bit word may not be sufficient for the accuracy we need in the future. How about even longer mantissa lengths in the future?
Mm-hmm. We certainly make a lot of compromises as we build machines, and I have a very difficult time in choosing the parameters that you're talking about. What I have done in the past is talk to that group of users of Cray machines who take their early machines, because I have to have the feedback soon, and ask them what they want. It was very difficult going from 60 to 64 for me, because everything I had done had been 6-bit oriented up to that time. But it seemed very clear that I was tardy in making that adjustment. And so that one was easy, because everybody told me to do it. In terms of, and one's complement arithmetic too, you know, way back there in engineering research, I was taught that arithmetic should be done one's complement. That was because it was so easy to make negative numbers. But I finally caught on to that one too. But in terms of finding the right combination between exponent and coefficient, we got started down this road just quite a long time ago, and I'm not hearing enough reasons to change it now. Now, it may very well be awkward, but I'm reluctant to make a change just because of history, our local history. Don't think in a technical sense we would gain much with a different format there. So I doubt if it will happen soon. I think we have to stick with what we have for at least another generation.
Longer word lengths?
Longer word lengths are a problem in terms of utility. Here again, there are a group of people who clearly would like not to use double precision. I mean, we can obviously do longer wording. But if you look at the total amount of work being done, there are at least an equal number of people that are quite insistent on having 32-bit words because they can use their dollar investment so much more efficiently. And so it seems like, and it's hard to have these options all at once. There's a real sacrifice in performance when you put options on word length. So it seems like 64 is the best compromise between the voices I hear, if you understand my position.
Don Lee, one of the first programmers ever, told me this story. In the 1960s, a 1604 programmer from the University of Illinois decided to make a pilgrimage to Mecca. Control Data had built a small lab in the farm country outside of Chippewa Falls, Wisconsin, for Cray to use. Seymour and 25 people interested in computers moved from Minneapolis to this small town to build the 7600. The way the story goes is that Don Lee's friend got lost and was traipsing around in the muddy fields looking for Control Data's Chippewa operations. He runs into a farmer and asks him where the Control Data facility is. He gets no response. He goes into a lengthy explanation, and the farmer doesn't know what he's talking about. In exasperation, he finally blurts out, "It's the place where they're building big computers." To which the farmer responds, "Oh, you must mean Seymour's place. Why didn't you say so?"
Well, Fred, we should have had this sex talk earlier. You know, love is a wonderful thing, a beautiful experience, if you're ready. But Fred, you're only 3, so you should wait until you're, well, older, because there's thousands of little Freddies born every day that are unwanted. Then they have to be put to sleep.
You can't stop your pets from acting naturally, but if you love them, you'll have them fixed. Call us. We can help.
Peninsula Habitat for Humanity, providing interest-free loans to build affordable housing in San Mateo County, needs your support. 4 houses in East Palo Alto are planned for completion this year. Each recipient will provide sweat equity labor to defray cost. Financial donations are urgently needed. Please send them to Peninsula Habitat for Humanity, Post Office Box 5493, Redwood City, California, 94063, or call 415-594-2266.
The Cray 2 was the first computer in which the electronics were completely immersed in liquid. The liquid was pumped quickly across the electronics to remove heat. When Greg Mansfield gave Joe Sykos his first look at the Cray 2, Greg leaned over, pointed out some small bubbles rising along the edges of the PC boards, and remarked to Joe, "This is a new way to do a bubble sort." In fact, this machine gives a whole new meaning to the term floating point operation.
My name is Jack Worlton from Los Alamos. I'm interested in the Cray 5. In particular, I'm interested in the physical dimensions of the Cray 5. Because if your cycle time is going down by a factor of 2 and your processor is going up by a factor of 4, you'll be up around 10 to the 12th floating point operations per second, and I'm interested in the size of such a device.
Yes, I wish I could answer that. I feel nervy enough talking about the Cray 4 right now. It is certainly going to be biological, right? We've got a few people working in that area, and I hope they can do it in another 4 years. It's going to be quite a struggle. The Cray 4 has a 1 nanosecond clock period, but as the Cray 3 does, it has a 2-phase clock. By that I mean in the Cray 3, we have to latch the data every nanosecond. Now, that's not much travel time, even if the circuits were infinitely fast. So in the Cray 4, we have only 500 picoseconds between latch times. So this is getting right down to where gallium arsenide is important. And beyond that is a little hard for me to envision. I do think we need another material by then.
You just mentioned other materials. Two questions. What do you think about indium phosphide and some of the other 3,5 compounds? And what about some of the things that lesser mortals like IBM have not been able to conquer, such as superconducting materials?
Well, indium phosphide certainly is the thing in communication now, and therefore one would expect it to be a next step in terms of electron mobility. But is electron mobility really the issue? And it isn't right now in gallium arsenide. It's the insulating property that has the greater advantage over silicon. One of the things that's happening, and particularly in the communication area, is that putting epitaxial layers of indium phosphide on silicon, which is fine for that purpose, but the capacitance goes right back up. And so as I look at epitaxial layers of better materials on silicon, I find the capacitance problem really negates it, and that's too bad.
What about the second half?
Superconducting materials, I don't see how to use. I mean, other people are exploring cooler things, and that's great. It doesn't seem to me I should try to do what other people are doing. I'm trying to find a unique path to make a unique contribution, and so it has to be a narrow one. And I think I've got all the nerve I can muster right now for the gallium arsenide.
Roger Hockney, University of Reading. The limitation on performance of many of the computer systems, particularly of the Cray 2 actually, is the performance of memory. You've told us a lot about how the logic's been improved with gallium arsenide. Can you see or say anything about improvements of memory access speeds?
Yes. There is a big improvement in the Cray 3 over the Cray 2 because memory circuits are progressing very rapidly still today, and I hope they continue to. The Cray 2 used, at least the early ones, used dynamic memory parts, which were very slow, like 120 nanosecond access. And the Cray 3 uses static parts that are the same size, weren't available then, but are now, with a 20 nanosecond access time. So there's a dramatic increase in speed due to the rapid evolution of memory technology in silicon. So I think that the memory in the Cray 3 is keeping pace. And in fact, we see fewer conflicts with a 16 processor Cray 3 than we did with the 4 processor Cray 2 because of that big increase in access time and cycle time of the static memory parts.
Thank you.
Chris Norrie, Amdahl Corporation, Sunnyvale, California. You're on a very fast cycle time, and making machines small must help a lot of the problems. Nevertheless, one of the beasts you must struggle with is clock skew. How limiting is clock skew, and how do you overcome those problems?
And here's a real engineer, yes. People who talk about clock skew know what they're doing. Yes, clock skew, of course, is always a challenging problem, and it is the reason that we moved from a single-phase clock in the Cray 2 to a two-phase clock in the Cray 3. With a two-phase clock, you can use a wide clock pulse. In fact, it is half of the clock period. And so you pay the price of having twice as many latches with a two-phase system, but you have much broader clock tolerances because you can have overlapping then between the two phases of the clock. And the result is the clock skew has to be only slightly better in the Cray 3 than it does in the Cray 2. And with the gallium arsenide clock fan-out modules, we have much tighter control of the clock. So we seem to be in better shape, surprisingly, with twice the clock rate, but with the two-phase system. Now, with the Cray 4, we'll be pushing it again. We'll be pushing very hard, and clock skew will be very, very important. But I don't know enough about that yet to tell you how tough it is.
Thank you.
Burton Smith, Terra Computer Company. Have you caught any Colorado trout yet?
Pardon?
Have you had a chance to catch any Colorado trout yet? Colorado trout.
Oh, trout.
Trout fishing.
Well, I've been up in the mountains every weekend and walking along the stream, but I don't have a pole.
I'll loan you one.
Steve Wallach, Convex Computers. In the same vein as the skew, how do you debug a circuit that is so small when you put a probe on it, you tend to alter the capacitive structure of the circuit, and therefore you may lose exactly the thing you're trying to find?
Yes, and I'd like to answer that in two ways. How do we do it initially when we're debugging a machine, and how do we do it when the machine is assembled in the field? Because they are different problems, both serious problems. The way we do it in terms of development is we test the modules individually, and they're very big. They're a quarter of a processor each. We test them individually in a dry environment with what we call a pulse power supply. That is, power is turned on very briefly, like for a millisecond, and then is turned off for a long time so the module doesn't overheat. But this occurs repetitiously, and so one is able to run the circuits at high speed for a very brief time, but brief time being thousands of clock periods. And therefore, we can then mount these under a microscope, and we have micromanipulators to bring in probes, and we touch the ends of those 12,000 jumpers. And they give us a lot of information, too much in fact, because you can spend a career there with your micromanipulators looking at pictures. But with 10,000 ohm probes on a micromanipulator with coaxial leads coming off them, you can get quite good pictures. And we get typically 300 picosecond edge times into the oscilloscope that way without really loading the circuit too much. The circuits are 50 ohm impedance load. So if you put a 10,000 ohm probe on it, it isn't bad. So that's how we do it in the development phase. In the application of doing maintenance in the field, what we do is simply induce or deduce from the external things 3 computers away. We have to deduce which module is bad, which isn't all that tough because the processors are largely bit-oriented. Only have to determine which quarter of the word is wrong and take the module out, and then you put it dry again and you do the pulse power supply testing. So that's the vehicle. If it weren't for the dry mode of operation, it would be very difficult indeed. Have we done it?
That's it. Thank you.
Thank you very much.
I have some Cray stuff to show you. In chronological order, I guess, we start off, we saw this manual from the 1604 in an earlier program with Seymour's signature. I don't have any parts from the 1604 anymore. I thought I did, but my inverter seemed to be lost. This is a module called a cordwood module from the 6600. You can see it's made from 2 circuit boards, and there are transistors, discrete transistors in little, I don't know, they're small cases anyway, mounted on the circuit boards, and then they're mounted, they have test points come out here that are all shielded, and this is what the 6600 was built from. 6600 drove storage modules, which looked like this. This is a storage module from a 6600, and I haven't worked with that machine in a long time, but if memory serves me right, this is 4K of 6 bits wide, I believe. I think 2 of these make up a PPU memory. Anyway, you can see, and here you can see the little toroids and stuff where, well, let's see, it's very difficult to see. Little toroids in here where it drives the core. You can see the transistors and stuff built on the boards. And inside this, there's core memory, though we don't want to open this one up. After the 6600 comes a 7600, and I have a 7600 module here. And the 7600 module is closed. It has many circuit boards inside. I believe as many as there are pins here to plug it into the backplane, which is 1, 2, 3, 4, 5, 6, 7, 8. 8 cards. And an example of a card, well, you can see the test points while I have this. Right here, there are test points which, again, are shielded, and you can just stick your test probe in there and measure one of many signals. Here we have an example of the 7600 card. Again, you can see the transistors here, little toroids, so I assume this probably was something to do with core memory, although I see some other little tiny toroids here. And lots of resistors, and I don't see any diodes. And that drove a memory module, which is like this. This is a memory stack from a 7600, which Bob Zaleski was kind enough to loan to us for this show. And I don't know if you can see, but it's a stack, and there are many core planes. I have a core plane right here, a single plane that goes in here like a deck of cards, and where these tiny little wires cross, and I'll try and make it reflect there so you can see the wires a little bit. Where the wires cross, each one of those has a tiny, tiny little magnetic core. So that was about as advanced as magnetic core memory got. Well, be sure to tune in again next week at the same time for High Tech Heroes. Zai Qian.
Thank you for joining us this week for High Tech Heroes. Be sure to tune in again next week when we will bring you more entertaining information about the people and ideas behind the scenes in today's high-tech industry. And now, this is your announcer, Bill Weigel, wishing you the best of luck and a pleasant week. Au revoir.
Videotaped lectures of many industry leaders are available from University Video Communications of Stanford, California. This episode of High Tech Heroes has been made possible in part by grants from Supersoft Incorporated of Sunnyvale, California, Kinetic Microscience, San Jose, California, Cybernetic Arts, Sunnyvale, California, Big D Closeouts, Sunnyvale, California.